In 1969, scientists thought they had solved one of Earth's greatest mysteries when they analyzed the first samples of lunar rock. The moon, they discovered, was bone dry, which seemed to confirm how special Earth's water really was. 55 years later, we've discovered water in the most unexpected places, locked inside asteroids, hidden in lunar soil, even manufactured by the sun itself. These findings are rewriting the entire story of how water moves through our solar system, and the implications are staggering. The answer to where Earth's oceans came from has taken us from the sterile laboratories of NASA to the ancient rocks of space, from the frozen poles of the moon to the heart of distant comets. Each discovery has revealed another piece of a cosmic puzzle that spans billions of years, and nowhere has this search been more revealing than in the remote deserts of the American Southwest, where scientists have been quietly revolutionizing our understanding of water's journey through space. The asteroid hunter's discovery. Dr. Dante Loretta stands before banks of computer monitors in the University of Arizona's Lunar and Planetary Laboratory, watching as 7 years of preparation culminate in a stream of data that will rewrite textbooks. The OSIRIS-REx spacecraft has delivered the largest sample of asteroid material ever collected by human hands, and the first analysis results seem impossible. Bennu, this ancient pile of rubble drifting through space, contains far more water than any computer model had predicted. The asteroid formed 4.6 billion years ago from the debris of a much larger parent body, and somehow it has preserved water molecules within its rocky matrix all this time. The samples reveal water concentrations reaching 17,000 parts per million by weight. Nearly 2% of the asteroid's total mass exists as water locked within clay minerals. Advanced mass spectrometry techniques dissect the isotopic composition of this ancient water molecule by molecule, and the deuterium to hydrogen ratio tells a story that reaches back to the solar system's violent birth. These measurements show that Bennu's water formed not in the cold outer reaches of the solar system, but in the warm inner regions where Earth itself coalesced. The water molecules became trapped within phyllosilicate minerals as the asteroid's parent body underwent aqueous alteration, a process where liquid water chemically transformed the original rock into clay-bearing minerals over millions of years. The laboratory results challenge everything scientists thought they knew about water distribution in the early solar system. Previous theories suggested that water-rich asteroids formed only beyond the frost line, that imaginary boundary past Mars where temperatures dropped low enough for water ice to condense. But Bennu samples proved that substantial quantities of water existed much closer to the Sun, incorporated into the very building blocks that would eventually become the terrestrial planets. Mission scientists realized they are holding physical evidence of the cosmic delivery system that brought Earth its oceans. The isotopic fingerprint of Bennu's water matches Earth's oceanic signature with remarkable precision. The deuterium levels, the ratios of oxygen isotopes, even the trace concentrations of noble gases all point to a common origin. This isn't merely suggestive evidence. It's a direct chemical link between asteroid water and the water flowing through Earth's rivers and seas. The implications extend far beyond a single asteroid sample. Spectroscopic surveys conducted by ground-based telescopes have identified thousands of asteroids with similar compositions to Bennu throughout the inner solar system. These carbonaceous asteroids, designated as C-type in the asteroid classification system, represent the most primitive materials left over from planetary formation. They contain up to 20% water by mass bound within their mineral structures like molecular time capsules. Computer simulations using the latest gravitational models show how these water-bearing asteroids migrated inward during the solar system's chaotic early period. As Jupiter grew to its current massive size, its gravitational influence scattered countless asteroids from their original orbits. Many plunged toward the inner solar system, where they collided with the forming terrestrial planets. Each impact delivered not just rock and metal, but substantial quantities of water locked within clay minerals. The precision of modern analytical techniques reveals details invisible to previous generations of scientists. X-ray diffraction patterns show the crystal structure of Bennu's phyllosilicate minerals, while electron microscopy images reveal microscopic pockets where water molecules nested between layers of clay. Secondary ion mass spectrometry can measure isotope ratios with precision down to parts per million, creating detailed maps of how water is distributed throughout individual mineral grains. Laboratory experiments recreating the conditions inside asteroid parent bodies demonstrate how this water became incorporated into the rock matrix. When researchers subject meteorite samples to temperatures and pressures matching those found in asteroid interiors, they observe the same aqueous alteration processes that occurred billions of years ago. Water-dissolved minerals transported chemicals and precipitated new compounds, creating the complex mixture of hydrated minerals found in Bennu samples. The asteroid's water tells multiple stories through its chemical composition. Trace elements dissolved in the ancient water reveal the temperature and chemistry of the environment where it formed. The presence of organic compounds mixed with the hydrated minerals suggests that asteroids delivered not just water to early Earth, but also the carbon-based building blocks necessary for life. Amino acids, the molecular components of proteins, have been detected in Bennu samples alongside the water-bearing minerals. Statistical analysis of the sample data reveals that asteroids like Bennu could have delivered enough water to fill Earth's oceans many times over. During the late heavy bombardment period between 4.1 and 3.8 billion years ago, billions of these water-rich asteroids struck the inner planets. Each impact released the water trapped within clay minerals, gradually accumulating into the vast reservoirs that would become Earth's hydrosphere. The discovery transforms our understanding of how planets acquire their water supplies. Rather than relying on occasional comet impacts from the outer solar system, terrestrial planets receive their water from the same population of asteroids that delivered their rocky material. This process operated throughout the inner solar system, suggesting that water delivery was not a rare event but an inevitable consequence of planetary formation. The OSIRIS-REx mission has provided the first direct proof that asteroids served as the primary water delivery vehicles in the early solar system. The samples represent more than scientific curiosity. They are fragments of the cosmic process that made Earth habitable. Every drop of water on our planet carries the isotopic signature of these ancient asteroids, connecting us directly to the violent period when worlds were still forming.